Welcome back to the next video, everybody. Today, we're going to continue collecting results needed to prove solvable n equals 2 Langland's reciprocity. We're going to gather the results of the symmetric square lift and the Rankin-Selberg product result. So first, we need a little bit of Lie theory. So let G be a Lie group. So you're thinking smooth manifold, that's a group, and operations are compatible with the manifold structure and things like that. There's a Lie bracket and so on and so forth. Okay, we'll let big psi from G to the automorphisms of G be given by G maps to lowercase psi sub G, where lowercase psi sub G is the inner automorphism map from algebra class. It sends H to GHG inverts, the conjugation by G map. Okay, big psi is a homomorphism of Lie groups. We'll define add sub G from the tangent space at the origin of G to the tangent space of origin of G to be the derivative of big psi sub G at the origin of E. In other words, it's just the induced automorphism of Lie algebras, and it's a group homomorphism from frac G to frac G, where frac G is the Lie algebra of big G. So remember, if you think of your Lie group as this kind of manifold here, and you think of E as the origin here, the Lie algebra is like the tangent space to G at E. Okay, so there's always like this derivative map every time you have a homomorphism of Lie groups like this. Now I can form a homomorphism, which I'll call add from G to the automorphisms of the Lie algebra. And what is that map? It just sends G to add sub G. This is called the adjoint action or the adjoint representation of G. This is some basic Lie theory, okay? So here's the setup for symmetric square lifting. We'll let A be the three-dimensional representation of PGL2 of C, determined by the adjoint action of PGL2 of C on the Lie algebra of SL2 of C, okay? If you know your Lie theory, if you're comfortable with the previous slide, and if you do a little bit of digging into various Lie algebras and various Lie groups and which Lie algebras they have, and so on and so forth, you end up with the following diagram of representations. You have an add map from GL2 of C to GL3 of C. Then you have A, the map that I'm talking about on this slide, and then you commute the diagram with the natural map from GL2 of C to PGL2 of C, just the mod by scalars map. Okay, now, this add here can actually be thought of as a morphism of the L groups of GL2 and GL3, it turns out. Okay, that's what we're going to need to realize going into the next slide, the theorem of the symmetric square lift. Okay, so brush up on your Lie theory, make sure you understand this diagram. It all comes from this slide up here. Okay, so theorem 7, here's the theorem of the symmetric square lift from GL2 to GL3. To each cuspidal automorphic representation pi of GL2 of the adels of F, F is our number field we're working over here, there is an automorphic representation big pi of GL3 of the adels of F, such that for almost all places V, the local Langland's class T sub big pi sub V is just add, thought of as a map of L groups, of the local Langland's class T sub lowercase pi sub V. So this lift of this cuspidal automorphic representation sort of preserves local Langland's classes in the sense that the add of one is the other. Now, this lift, so is this cuspidal automorphic, this lift? Well, the lift of pi to GL3 is cuspidal automorphic unless pi is monomial. Now, this is a term we've defined already. Let's define it again. What I mean by that is it's of the form pi of sigma, where sigma is a character and sigma is induced from a Hecke character of some quadratic extension. Okay. Now, if you want to see a proof of this, you can see Galois-Jacquet, a relation between automorphic forms on GL2 and GL3, and you can also see Shimura on the holomorphy of certain Dirichlet series. Okay, so we will use this result in the proof of n equals 2 solvable Langland's reciprocity. Okay, we're going to need one other theorem, the Rankin-Selberg products theorem. Here's the setup. I can certainly view for whatever k, GLK of C as the L group of GLK. And I can view GLN of C cross GLN of C as the L group of GLN cross GLM, of course. Now, there's a natural L group morphism rho from GLN of C to GLM of C to GLNM of C, and it's given by the tensor product. Okay, so I have a natural morphism of L groups given by the tensor product. So theorem 8, Rankin-Selberg products. If I give you cuspidal representations, pi on GLN and pi prime on GLM, then let's let LS of S pi cross pi prime denote the partial L function given essentially by tensor product of local Langland's classes. So we're taking the product over places V naught and S of the determinant of I minus the tensor product of T sub pi sub B with T sub pi sub prime sub B times Q to the negative S inverse. This is the usual L function, partial L function setup. Okay, it's given by the tensor product. Two things are true. This L function extends to a meromorphic, it's just defined on a right half plane, right? But it extends to a meromorphic function on C with functional equation relating the value at S to the value at 1 minus S, as L functions often do. L functions often do things like this. This is often a desirable property for L functions to have. Okay, also, we like when L functions have Euler products. Ls of S pi cross pi prime completes to an Euler product given by the product over all places V in whatever field we're working over of Ls, kind of these local L functions, Ls of pi sub V cross pi prime sub V. Okay, so we can write the global L function as a product of local L functions. In other words, across all places V. Now, this is holomorphic on the right half plane, real part of S bigger than or equal to 1 if M isn't N. If M is N, this guy has a pole at S at any S with real part of S equals 1, if and only if the absolute value of the determinant map to the S minus 1 tensor pi is nothing but the contragradient of pi prime. In other words, the dual representation of pi prime. Okay, so some closing remarks. Where would you go for a proof of this? Jacquet, Shalika on Euler products and the classification of automorphic representations 1 and 2. And then I'm not sure how to say Moglin and Waldspurger. They have a paper as well. And we actually don't need this broad result here. We're just going to need the case n equals m equals 3. Okay. And then I'll just close by saying there is one more instance of Langland's functoriality we're going to need to collect to actually finally proceed into the proof of Langland's reciprocity, other than the 3 we've looked at so far. And this is the theory of so-called base change. It's one of the more important instances of Langland's functoriality we'll need. We'll discuss that in the next and final video on this collection of results kind of spree that we're on, and then we'll finally get to the proof. All right, so I will see you tomorrow, and thanks for watching.